Hi folks, I'd like to talk to you a little bit about the electric field and the magnetic field and how they're similar, some of their similarities and some of their differences. So this picture right here represents a positively charged particle. And the field lines around a positively charged particle are symmetrical and they radiate outward. And again, what these field lines tell us. They basically tell us the field direction is probably the most important thing. For example, at this point right here, the electric field points this way, parallel to the field line. And what that means in turn is, if I put a proton here, it will feel a force in that direction due to that electric field. However, if I put an electron here, it will feel a force in this direction, up into the field. Now, this is an example of what's called an electric monopole. Mono is just a fancy word for one. If I take this positively charged particle and I put a negatively charged particle next to it, the field lines tend to look like this. The reason they look like this, well, in this region the field is relatively strong. That's because the field, due to the positive charge, is to the right, and the field in this region, due to the negative charge, is also to the right. So they add. We get a really strong field in this region. Okay? Now this should look somewhat familiar to the picture that I had up for a bar magnet. The field produced by a bar magnet looks something like this. So, again, when I talk about these magnetic field lines, if you think back to the video where I produced some around a magnet. Magnet and these iron filings, they line up with the magnetic field. Hopefully you can see that in the video. Okay. You can see that these filings actually line up in these lines, and they're mapping out magnetic field lines. So that's what these lines represent. You'll notice that the field line configuration for a bar magnet is virtually identical to the field line configuration for this pair of this positive charge and negative charge. Now over here on the right, this field configuration is called the electric dipole. Di for two, there's two charges here. For that reason, this field configuration is called a magnetic dipole, because the field configuration is identical to this. So there's one similarity. The field configurations for a bar magnet and the electric dipole are very similar. However, here's a huge difference. Over here, I can take this individual charge, move it a long way away all by itself, and I get a field line. We get field lines that look like this. A monopole field. That seems to indicate that maybe I can break the bar magnet in half and do the same thing. So imagine breaking this in half. And again, by analogy, it seems to be that, well, maybe I get field lines that look like this. Well, it turns out that you never do. Whenever you take a magnet, break it in half, what you get is a smaller magnet, with field lines running north to south, just like before. It's just weaker. And then the other half would give us field lines that look like this. Again, north to south. So here's kind of an important rule to magnetic field lines. There are no magnetic monopoles. There's no element of magnetism that scientists have been able to find similar to an element of charge. Now, people are looking for these things. One of the famous theories in physics these days is string theory. And string theory does seem to indicate, or at least point in the direction that there could be magnetic monopoles in nature somewhere. But at this point, nobody has found one. So I just want to talk a little bit about the nature of these fields and how the magnetic field is similar to the electric field and where it's different. Right?